Hello all, welcome back to Troubleshooting Python Application Development, where we are helping you make faster apps and apps that take less RAM to run using various Python modules and strategies. We're starting a new section today about making our apps run faster with parallel programming. So what is parallel programming? Parallel programming's idea is we split the program into smaller parts, and we run each part on separate cores of the CPU, and we combine the end results later so that we can run things twice or 4 times or even 16 times as fast, depending on how powerful your CPU is. This paradigm extends to GPU programming, so if we're having a graphics card, a very popular technique nowadays with cryptocurrency mining and machine learning is to parallelize our operations and run it on many cores on the GPU and combine the results afterwards, and that will provide a very good performance increase for a manageable amount of code. So we're going to introduce parallel programming in 5 different videos. We're going to first start by talking a little bit more about what parallel programming is about. We'll then talk about doubling our speed of list processing with tuples. We then talk about easily speeding up a group of processes with pool. So that's a submodule in the multiprocessing module in Python. We then talk about stop processes from interfering with each other with locks. So this is how we make sure that we can work on the same data between different processes but still have them not overwrite the results from one another. In the last video we're going to talk about logging. So logging different processes when they're all running at the same time is a little bit more tricky, so we'll also talk about how we can make that happen. First things first, let's have a quick chat about what parallel programming is about, the core concepts. We're going to talk about this in 3 different steps. So we have what is parallel processing, and then we talk about embarrassingly parallel programs and less embarrassingly parallel programs, and then we talk about the global interpreter lock of Python. So with parallel processing using multiple cores, we can increase the speed of our programs by dividing a problem into independent subunits and using multiple cores in our CPU to solve those subunits in parallel. Parallelism is necessary for large-scale problems. It's very unlikely that one computer can do enough work in 24 hours if you're dealing with truly large-scale applications. Some problems are known as embarrassingly parallel problems. These problems are where the subunits are completely independent of each other, so it's very easy for you to divide the problem into multiple subunits and give one each to the cores. One example of this is if we have, let's say, a CSV file and we need to combine each row of the CSV to produce a new result. This is quite trivially parallel, right? We can just say the first 20% of the CSV file goes to this core, second 20% goes to the other core, and that's very easily distributed within 5 cores, and they can all run, and theoretically your program should run in 1/5 of the time plus the overhead you need to parallelize and distribute the workload, and also to combine the workload at the end. Some other problems are less embarrassingly parallel. For example, if they need to work on the same resource, or they need to do some I/O and other complicated operations, this is less straightforward to implement in a parallel programming sense. And so what we're going to present in the next 4 videos are strategies on how we can make both embarrassingly parallel problems and less embarrassingly parallel problems into a parallel processing paradigm. The last thing I want to talk about is the global interpreter lock of Python. You might hear this referred to as the GIL, and while Python can spawn and handle threads, threads don't necessarily increase the performance of your app, because the Python interpreter using the GIL, one Python instruction is allowed to run at the same time. So if one thread executes a Python statement, then the GIL belongs to that thread and all other threads are paused. And since the lock, or the global interpreted lock, can only be acquired by one thread at a time, other threads are prevented from executing Python statements while they don't hold the lock. So creating threads don't necessarily, or even don't entirely, increase the performance of your Python apps. On the other hand, if we are using parallel processing, where we are paralleling processes instead of threads, processes don't share the same memory area in the OS, and they're independent from each other, and each process has its own GIL, so we can sidestep this constraint of Python. And while processes have a few constraints, like starting up new processes are slower than starting up new threads, they consume more memory overall, and inter-process communication can be cumbersome because you need locks and other locking mechanisms to make sure that you don't overwrite. Different processes don't overwrite the same content. Python provides a lot of good frameworks to allow you to tackle embarrassingly parallel and less embarrassingly parallel problems with processes without dealing with too much of this overhead. And that's all there is to it. Those are the three main blocks of learning parallel processing. We need to know that parallel processing is dividing a problem into subunits and distributing these subunits to different cores. We have problems that are easily parallelized and some problems that are less easy to do that. And because of the global interpreter lock, we can't only distribute the task into different threads, we need to distribute it to different processes for us to actually be parallel.